Hey folks, it's the old MAT guy again. It's Nat. And this time I got a Wacom pad. Yes, this is a Wacom pad. And I have a new display so that I can show you the question while I'm working. Isn't that great? Yeah, that's great. Let's look at the question. The question says we have two functions, f and g, which do some certain operations. The question is about the set of positive integers that can be achieved by applying in some order a combination of f's and g's to the number 1. Well, isn't that interesting? So I have gone through that before because I studied binary. Thank goodness, because now we have the binary expansion of 100. So let's write down 100 here. Great. So any computer geek will know how to convert decimal numbers to binary, but some hardcore computer geeks won't. So anyway, for all of us here who don't know how to compute binary, or if you do know how to compute binary, then this will be a refresher. So what we do is that we divide by 2 to get 50, and then we write down the remainder on the left. So we have a remainder of 0. Then we have 25, 0. We divide by 2. Yes, there's a remainder. 12, you get 1. 6, 0. Then 3, 0. Then we don't put 1.5 because again, we got a remainder. And since there's a 1 here, we can write an arrow here and get a 1. We read these remainders from the bottom to the top, giving us 1, 1, 0, 0, 1, 0, 0. There, isn't that great? Show that 100 is an S by describing explicitly a combination of F's and G's that achieve 100. Now what do F and G actually do? Let's write down F. What this is telling us is that it's appending a number to some binary string. So let's say your binary string is, I don't know, S. It could be a number, it could be the source code of a video game, I don't know. So what your F is doing is you're appending 1 to S. So that means your number will get doubled and add 1 and your video game will get broken. Now how about G? N equals to 4n. This time it's taking S, and what it's doing is turning it into S, 0, 0. Again, your video game is broken and your numbers quadrupled. Well done to you. So, show that 100 is an S by describing explicitly a combination of F's and G's that achieves 100. You notice there is 1, there's a 1. So let's write an F here, then an F. Then since there are 2 zeros in a row, we write a G. Then you continue this procedure. So that means it's F, F, G, F, G, 1. There, we have it. Show that 200 is not an S. To double a binary string, we append 0. So 210, that's how we write it, is 11001000, because we are appending a 0 on the end of the binary string, because binary space 2. So we write a big 2 here. Now we use the same procedure, F, F, G, F, G. But wait, there's a lone 0. So this lone 0 is not accounted for in any of the two functions. So you can't just square root G or use a half function because that's cheating. So, hence, 200 is not in S. Question 4 is quite simple. Let's scroll down a bit. Seriously? Great. Show that in N is in S, there's only one combination of applying F's and G's in order to achieve N. So this is the same as saying that there will be only one combination of F, 2n plus 1, and G, let's say it's 2n instead of 4n. Then there's only one way, and that is the binary expansion. Similarly, in you have F, G, and H, where H is 2n plus 2, you get hyperbinary. And there is no way that actually more than one, but how do you represent it uniquely? I don't know. Only the numbers which have ones in them in hyperbinary. So that means the numbers like 1, boring numbers like 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1. It's quite a fun number system. In fact, I've done a Word document on it. I might show you later. So, show that if n is an S, there's only one combination of this. So that means, let's say your S, your good old S, your binary string is 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1. Great. So, that means you can go 1. And then you have an F, then G, G, F, G, F, F, F. Which reminds me, I think I see an error in here. Let me try scrolling up again. Ah yes, the 1 was an 1, not an F. How silly of me. Should be an F, G, F, G, not F, F, G, F, G. Moving on, we now have F, G, G, F, G, F, F, F. So there goes our uniqueness proof. Let's screw up to number 5. How do I screw this thing? Yes. Let UK be number of the elements n of S that lie in the range 2k to 2k plus 1. So basically, we're telling of the numbers which have 1s. Yes, 1s. All numbers have 1s in binary except 0s. And 2 zeros in a row. So let's write them down for... Let's say people and pretend to write 2 to the power of 3 to 2 to the power of 4. So we're asking for all the binary strings with 2 cubed to 2, 4, which 8, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Again, we cancel out the ones which have 1 zeros in a row. Yeah, great. So we have an odd number of zeros in a row. Nope. So then again, we now have 1, 2, 3, 4 sets which fit this rule. Show that this. So what is this telling us? It's saying that UK plus 2 equals to UK plus 1 plus UK. So where do the factors come from? So UK plus 1 is, that means you add a 1 to the end of each string. So effectively adding 1 to the length. And UK, which means that you have to add 0, 0 to the end, which is therefore making it the same length as UK plus 2. So we are having fun with binary strings right now, is it? Well, the fun doesn't end there. Let SK be the number of elements of S that lie in the range 1 to n to 2k plus 1. So again, SK plus 2 is a bit special. So SK equals to the sum of 1 to 2k plus 1. So therefore, we have is UK plus UK minus 1 plus UK minus 2 plus dot 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 plus U1. Then we are now saying that SK plus 2 equals to SK plus 1 plus SK. So SK plus 1 equals to UK plus 1 plus UK plus dot 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 dot, and then this is UK plus dot 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 plus U1 plus U1. And then don't forget, we have the 1 at the end. What does this show us? This means that we are also taking into account, and this is kind of strange, that gosh, these Wacom pads. UK equals to SK plus 1. Wait, that's the wrong identity. Let's try a second guess. So we have SK's UK plus 1, UK plus 2 plus dot 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 dot. So now guess what this means? We have an extra 1 string. And that 1 string just happens to be 1. Yes, 1. That's it. And we prove the last statement. Now let me continue on a short digression to another numerical system that probably none of us will ever learn about in school or even in the MAT. In young mind like me who likes to put mathematical structures into everything, then you might have heard of obscure numerical systems like the one I mentioned before, hyperbinary, and then which has, wait for it, 0 and 1, and it also has the number 2. So it's like place carrier notation in binary but on steroids. So you have this 2 in the mix. The number of sequences you can have is the Stern-Brokow sequence. Yes, the Stern-Brokow sequence is basically the number of representations of hyperbinary, though it links to a different area of maths altogether. So it basically tells us, so we have S, the Stern-Brokow sequence is S1, S2, S3, say. Now we have S1 over S2, S2 over S3, S3 over S4, dot, 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 dot. And here's an amazing theorem. The amazing theorem is this set of fractions right here is the set of fractions which are irreducible with no repeats. And how does this have to do with a binary number system on steroids? I don't know. But who knows, I may make some hyperbinary tokens for you. In fact, I may well draw some for you. So we have 1, 2, 2, 4, 4, and this is a fun game to play with your friends, and you got some loose change in binary coins. So don't forget to print the screen and probably, and guess what? Play with these hyperbinary tokens and then say, you got some loose change. And then he hands you, wait, what's this? 254 cents. Let's say 1 is 1 cent, 2 is 2 cents. And then people will say, that's not real money. That's hyperbinary money. Okay, they might not know what's hyperbinary money. But anyways, you might like to research up on this wonderful and amazing number base. Oh, and don't forget the other obscure number bases too, like balanced ternary, balanced quinary, balanced decimal, balanced binary, if there is one. Yes, I may rattle on about this for decades, but as you know, I have business to do and I am currently completing a music degree. See you!